Alright, so here are your notes over double replacement reactions. We talked about single replacement reactions in class. Double replacement reactions are last reaction type. The notes are there. Let me go ahead and give you a second to copy those down, and then we'll talk about what they mean. So go ahead and pause the video right here. Okay, so let's talk about what these notes mean. Double replacement means two aqueous solutions of ionic compounds are combined, and then the positive ions just trade places. So if I look at my example, I've got potassium chloride on the left, and that's aqueous, and so that means I have a solid potassium and positive potassium and a negative chloride, and they're together in an aqueous solution. And then with my other reactant, I have positive silver and negative nitrate, okay, and that's also an aqueous solution. So these would be like water solutions. So these would be like the solutions that we use to react with the metals in the single replacement lab. So you can't see anything; it just looks like liquid water, or it might have some color to it, but it's going to be clear. That's what aqueous means. Now, when they come together, though, it says the positive ions trade places, so that's the first thing that we have to understand. Or I guess I could have done that in yellow. The positive ions are going to trade places, so the positive ions in the first compound, or the positive ion in the first compound, it's always going to be the metal. It's always going to be the one that's listed first. So that would be potassium, and then the chloride would be negative. And then what about on the other side there? We have AgNO3. What's our positive? Okay, should be silver. All right, and our negative is nitrate. So if we have the positive ions trade places, it's kind of like they're trading dance partners or whatever you want to call it. The potassium is going to trade places with the silver, and so the potassium is now going to be paired up with the nitrate. So we're going to get KNO3, and we have to think about charges. Potassium, though, is +1, nitrate's -1, so we don't need any more subscripts. We did carry the 3 over on the nitrate, but that's because it's a part of nitrate. We can't change that. So, and then our other product is going to be, go back to red here, silver would be paired with chloride. And I do want to look at charges once again, but silver is +1 and chloride's -1, so again, I don't need any further subscripts. Now, figuring out exactly what our products are, in this case, we have potassium nitrate and silver chloride, is kind of the easy part. We just traded the positive ions with each other, so potassium and silver traded places, and we figured out the charges and therefore the formulas of our two products. The somewhat harder part is this last bit. It says the reaction only occurs if one of the products is insoluble. And the word insoluble just means that it won't dissolve in water. So how do we figure that out? We go to the solubility rules, and this is on the back of your blue periodic table. But if I look at my solubility rules, the way they work is pretty much, it's pretty straightforward. Oops, let me zoom in a little bit on this. Okay, sorry about that. So it's pretty straightforward. Essentially, one of these two products has to be insoluble, meaning that it'll form a precipitate, which is that white or maybe yellow or some other color cloudiness that we get when we put together two clear solutions. We talked about on the first day when we talked about evidence of reactions. So if I look at my first compound, I have potassium nitrate, and potassium nitrate ends in NO3 nitrate. So it's an example of, it's an example of a nitrate. And if I go down to my list, down below, I can see that I have a rule for compounds that contain the nitrate ion. And that rule is that they tend to be soluble. And that's going to mean aqueous. That's going to mean that there's no precipitate of any nitrate, because there are no exceptions to that rule. So anything that ends in NO3- is going to be aqueous, and so it's not going to be a precipitate. So far, my first product is aqueous, and so far I don't really have evidence of a reaction having happened here. So I'm going to look at the second compound that formed, silver chloride, and so now I have to go to the rule for chlorides. And the rule for chlorides is, and again this is all in the back of your blue periodic table that you're given in class, the rule for chlorides is, just like fluorides, bromides, and iodides, they tend to be soluble, okay, with these exceptions. And notice silver is one of those exceptions. So what that means is my compound, my silver chloride, oops, didn't mean to cross it out, my silver chloride is an exception to the rule that says chlorides are usually soluble. Okay, so silver chloride, unlike most chlorides, is not soluble, so therefore it's going to be a solid precipitate. And we have to have one of our products be insoluble, be a solid precipitate, otherwise we're going to say no reaction. So this is a reaction because we formed a precipitate. That precipitate is silver chloride. And so now that I know that it's a reaction, I probably want to look at it to make sure that it's balanced, but it looks like this one is already balanced. It's got one of everything on both sides. So maybe just kind of clean up some of these extra marks, and I'm pretty much done. I do want to do another example. So let's go through another example. I'll set my solubility rules aside for just a second. But let's do another example. Let's say we have aqueous barium chloride. And our products in these, by the way, or excuse me, our reactants rather, are pretty much always going to be aqueous. So you don't have to worry about figuring out those physical states. Those are always pretty much going to be dissolved in water. So barium chloride reacting with lithium sulfate. And that's going to be aqueous. Okay. So the first thing we want to do is figure out, like, what are our potential products. So I don't even need the solubility rules for that, I just need the charges. And all I'm going to do is have the positive ions trade partners here. So I'm going to get some barium sulfate, and barium is +2 and sulfate's -2, so I don't need any more subscripts. And I'm also going to get some lithium chloride, and lithium is +1 and chloride is -1, so we don't need any subscripts there either. Then we're going to go to see if it's a reaction or not. And to do that, again, pull out my solubility rules, and I'm going to go ahead and look up sulfates. So the rule for sulfates is that they are usually soluble, but notice barium, Ba2+, is an exception. So right away, I can tell that this is a reaction because my very first product is a solid. And then my second product, LiCl, lithium chloride, my rule for chlorides is that they are soluble. There are 3 exceptions to that, but lithium is not one of them, so this is aqueous. And you should get 1 solid and 1 aqueous every time it is a reaction. You're not going to get 2 solids. You could get 2 aqueous, and of course that would mean that it's not a reaction. Okay, so now there are going to be a couple more questions that pop up on the screen just so I can see how you're doing with this, predicting the products and balancing. Make sure you come to class with lots of questions if you have them. So thanks for watching, guys.